welcome to the webinar. Just leave some time just to let people come into the webinar with us, just for a moment. Make sure everybody's sound's working as well, which is often a problem.
Great to know where you are in the world. So get in chat. I'm in a very cold, rainy Herefordshire today.
I'm just down the road in Gloucestershire, which the weather's pretty much the same.
Yes. We often get. I get it first, and then you get it.
Yeah, that's it. Yeah, you can give me fair warning. It's on its way.
Yeah. That's right.
Right. Okay. Shall we introduce ourselves and get started? Do you want to go first?
I think so.
Yeah.
Okay. So I'm Amanda, and I think between the two of us, we've been in education, teaching in secondary classrooms for over 50 years, haven't we, Karen?
Yeah.
Yeah, getting old now, and every one of these grey hairs, I think. And this is one of our passions, maths and science, along with practical work and so on. We have written quite a lot of resources, and we'll show you some of those later. But first of all, I think we've got a little poll for you to do. So if you could do the poll when it comes onto the screen, that would be amazing. I think maybe.
There we go.
There we go. So on a scale of 1 to 10, with 1 being the least and 10 being the most confident you could be, how confident do you feel you are in embedding math strategies into your science lessons today? So we'd love to know. We will just be, we'll just be a moment. So have a go quickly in terms of that.
And then that'll give us an indication of where you are now. So it'd be quite
Yeah.
interesting to see the outcomes of the poll.
Yeah, so if you've just joined us, we've got a poll going on, and it would be great if you could contribute to that poll. And it's always interesting for us.
Yeah.
There we go.
There we are.
Okay.
Well, that's quite interesting, isn't it? So medium to high, I would say. Confidence.
Yes,
Yeah, which is
yes,
good. Excellent.
that's all
Well,
good.
hopefully you'll still learn something new from this session. So that's good.
Hopefully so.
Yes, I
Hopefully
think
so.
so. So
So
just very briefly, we just wanted to introduce some of our texts and resources that we've produced, didn't we, Mandy?
yeah, so Karen and I work together quite a lot. We're co-authors on all of these books. Grappling with graphs, it started with us, we were both like, oh, why can't our students draw graphs? So we decided to do something about it. And it's a teacher-facing resource. It's got CPD in it, basically, but it's also got lots and lots of student worksheets in it as well, with the answers, of course. The second one is fantastic for disciplinary literacy. Easy to just take and put it straight into your lessons. They're all curriculum linked. The third one is maths and science, and we're going to talk quite a bit about that and strategies that we've employed in there today. And the fourth one, and I can't count, that's good for a maths and science talk, isn't it? The fourth one there, Key Stage 3 Science now, loads and loads of questions, making sure students are basically ready for Key Stage 4, really. Great for cover
Yes.
with answers. So
Yeah, if
let's
you're
get
looking for
going.
cover, that's a good one. Yeah.
Let's get going.
Yeah.
So, maths and science, what are the issues that you've come across? What are the burning issues for you? If you could stick them in chat, that would be great. What are the issues for you in terms of maths and science in your classrooms? So let's have a quick look in the chat, what the issues are for you. Terminology, absolutely.
Yes, huge problem.
Definitely. Conversion of units,
Converting units, yeah.
absolutely. Can't do maths, yes,
Yeah.
yeah. Yeah,
Yes,
teaching
maths
maths.
anxiety is a huge problem, actually. There's lots of literature on maths anxiety if it's something you're interested in, and girls' confidence as well in maths.
Yes. And we've got knowing how to use calculators.
Mm,
That's interesting with the new calculators as well.
yes, the new calculator doesn't have an equals button, which is always confusing.
Yes, to me as well.
Mm.
And using graphs, lines of best fit, absolutely,
Mm.
and so on and so forth. Well, grappling with graphs would be great for those of you that were talking about graphs, because there's lots and lots of practice in there, and also research about why students find it difficult.
Yeah, that's amazing how we were really shocked how much research there is out there actually on it, isn't it? It's just having
Mm,
time to read through it. Hmm.
definitely,
Yeah.
definitely.
So one of the companies I work for is Pixel. I actually lead at Pixel on science from 4 to 18. And one of the things we do at Pixel is we look through every single examiner's report from every single exam board at GCSE and A level for all the subjects. And then we identify the issues that are across those subjects. And this is actually for A level in psychology, maths, biology, chemistry, physics, and economics. These came up as an issue at Key Stage 5. Key Stage 5. And the question we need to ask ourselves is which of those are a problem at Key Stage 4? And if you have a read through, just let you give you a moment to have a read through. Which do you think are a problem at Key Stage 4 as well? And the answer is all of them. And this is a problem for us. Is actually some of those are coming up from Key Stage 2. Converting units is something they do at primary school. And I think we leave it a little bit too late in science when they come to secondary school. And when they're changing over, and I think we need to be embedding that much earlier and reinforcing it much earlier than we do. But these are a problem at GCSE and A level, which means we do need to be dealing with these at Key Stage 3 and Key Stage 2 for those of you who might be joining us at primary or middle school level. But quite interesting, isn't it, when you think about it? And come up on multiple years as well. So these ones came up this year, but they've also been up on previous years too.
I think what's interesting for me is that actually maths has got a problem
Yes.
with those as well.
In
You know,
fact, I was at a training event literally just now. I'll pick up my piece of paper. I was at a training event just before this one, where I had to list issues that students are having in their mocks that they've just taken in November. And standard form, rearranging equations, and straight line graphs all came up in GCSE maths as a problem on their mock maths. So it's still an issue. Yeah.
yeah, yeah. So, if you've not come across this before, the Education Endowment Foundation, and we'll have a link in the chat to this. This is a great audit tool for personally, or for actually for departments if you're a department leader, to look at. This is just one of the pages, and I've highlighted the exemplary because that's what we're all aiming for, isn't it? And it's talking about planning how to introduce new problem solving techniques and ways of thinking, using worked examples, modelling thinking, and removing those scaffolds always, so that our pupils can become independent. And this concept of deliberate difficulty is introduced. Now we've structured our talk today to have a look at quite a few of those in terms of that. So that deliberate difficulty is this sort of gradual increment, gradually increasing that challenge so that our students don't feel dumped in it. They feel, empowered to have a go and try in terms of that. So I just thought I'd give you that. It works for science. Obviously, it is the science audit tool, but it works for maths as well, doesn't it?
Absolutely. And if you think about the teaching, if you've ever been into a maths lesson, you will notice they do that deliberate difficulty really well. So they will model how to answer a question. They'll do some together with the students, and then they'll get the students to work independently. And that will be structured in a way that those questions get increasingly more difficult as they go through. So they might do 15 examples, getting increasingly more difficult. Some students, they might say, oh, start at question 7 because they feel they're at a higher level. but that deliberate difficulty, being really clear on that. Whereas in science, what we often do is go through an example and then give them an exam question, which is going straight to the top level of difficulty without doing that little bit in the middle. So we're going to
Yeah,
talk about some strategies, aren't we, Mandy, about
yeah,
helping to
yeah,
support with that.
yeah, yeah.
Now, whilst we're doing all of that, there's a couple of things we'd like you to keep in the back of your mind. So one of those is called pedagogical content knowledge. And I don't know if you've come across this before, but pedagogical knowledge is knowing different strategies for teaching. So, for example, group work, thinking about using mini whiteboards, for example. You might do think, pair, share, lots of different activities and styles of teaching, standing at the front and talking to the students, imparting knowledge. All of that's pedagogical knowledge, ways we can teach. Content knowledge is knowing the knowledge itself, the biology, chemistry, physics, the maths, and knowing that yourself. But pedagogical content knowledge is something that Schulman came up with in the 1980s. And this is about knowing the best way to teach that content. So, what are the best analogies to use? What are the best manipulatives to use? What misconceptions might those students be coming to you with, and thinking about those whilst you're teaching? Now, if you're a biology specialist, for example, your pedagogical content knowledge for biology will be high, but you might not be confident teaching physics. So you might think, oh, actually, I don't know what the best analogies are for teaching electricity. I don't know what misconceptions students might come in, or all the misconceptions they might come into teaching electricity with, and how to deal with them. So I might not be aware of those. And this is the problem with maths in science. Quite often, we know the maths, we might be confident with the maths itself, the content, but we might not know the best way to teach the maths. And that's where our maths colleagues come in. And that's important for us to recognise that we might not be, and some people will be. So some people are physics and maths, for example. We might not have the pedagogical content knowledge to be able to teach maths and science effectively. We really need to liaise with our maths department on that to help support us. So that's something to think about first of all. The second thing to think about is something called Johnson's triangle, which comes from chemistry originally in the early 2000s. Johnson came up with this idea. And what he said is the fact that when we teach chemistry, we should think about three corners of a triangle. So, if, for example, we were teaching about burning magnesium in an open flame, then the macro level, the tangible level of that would be a student carrying out the practical, seeing the bright white flame that forms and the white powder forming at the end. So it's very tangible. They can see what's happening. It's very clear. Then we might jump to the representational. So we might give them the equation for what's going on. So we might talk about it's, 2 mg plus O2 forms 2 MgO. And we might deal with those two corners of the triangle. And what we forget is that as experts, we think about the third corner of that triangle, which is the submicro. So we will understand about ions, we will understand about particles, we will understand about the rearrangement that's happening. The fact that we're going from metallic bonding to ionic bonding and all this kind of thing happening. And we will be doing that subconsciously, but we will be doing that because of our knowledge. And what we need to do is be explicit with the children when we're teaching them and make sure we're covering all three corners of that triangle in order to help aid understanding. So that's how it works in chemistry. But this can be applied to biology and to physics, and it can be applied to maths in science as well. Because when we do maths in science, we quite often deal with the representational, obviously, because we'll be dealing with equations and things like that. We do look at the submicro because we'll be looking at what does each of those symbols mean? How do we go about rearranging the equation? So we think, clearly about those two corners of the triangle, but we don't think about the macro. So in maths, they will use manipulatives, they will use models to help support the learning and understanding that's happening. So if students aren't understanding ratios, for example, they might introduce ratio tables as a strategy to help support. They might introduce the bar model to help support, all of which are macro, they're tangible. They help bring that intangible element into something that's understandable and touchable. And that can help. So we need to think about what macro level understanding do we need when we're teaching maths and science. So a couple of things to keep in the back of your mind whilst we move on.
So, how often do we assume because students have learnt something in maths that they should be able to do it in science and apply it in science? I've been guilty of, of sort of tearing my hair out about that over the years. And this vaccination model, Karen and I laughed quite a bit when we
Yeah.
talked about this. But it suggests students get their vaccination, their maths vaccination, and all should be well.
Mm.
But of course, that isn't what
Yeah.
happens at all. And this, maths understanding needs to be reinforced. It needs to be contextualized, and it needs to be explicitly taught in science. This knowledge transfer needs a little bit of a push to make it actually happen from maths to science. And actually, our maths teachers, certainly in schools that I've worked at, have really appreciated the contextualisation of the pure maths, if you like, and they've appreciated having sort of starter questions with the answers based in a science context that they can use to get their lessons started.
So,
So
so if you've ever sat there in a lesson and thought, you've learnt this in maths, why can't you do it? You are relying on the vaccination model of maths, the fact that they've been vaccinated in their maths and therefore they must be able
yeah,
to do it with
yeah,
you in science.
yeah,
Love
absolutely.
it. Love it.
So here's another insight in terms of transferring knowledge, and I'll just give you a moment to read that because it's quite a
Mm.
long slide.
It's always good to quote yourself, isn't it, in a presentation?
Oh dear.
Mm. So
So
what this is basically saying is that when students plot graphs in maths, they think about it in terms of X and Y. When they do equations in maths, they think about it in terms of X and Y. So maths is about X and Y. It's that, as Mandy was saying, it's that pure element. We're not thinking about units and things like that. It's kind of like pure maths. But when they come to science, it's more about the laws and the equations. So when we're plotting a graph, for example, we're thinking about what the labels are on the graph. We're thinking about the units. We're thinking about the relationship between those. And we're not thinking about X and Y. And what it's also saying is that even if a student is really, really good at maths and really, really, really good at physics, they still find it difficult to transfer knowledge and understanding between the two. So again, back to that vaccination idea. Even if they've had all the boosters, they still struggle to pull that knowledge and understanding across into other subjects. And it's not just science, actually, it's geography, psychology, economics, all of those other subjects as well, they struggle to transfer.
yeah, and a lot of the time they just see a graph at the end of an experiment as just
Mm,
something you do. They don't see why they've plotted the graph. They just think it's something you do in science. And if we're not explicitly using those to interpret patterns and trends and anomalies and so on, then we're missing a trick there, really.
definitely. Yeah. So basically that's covering kind of the theory behind what we're going to talk about. We're going to move into different strategies and things like that that you can use. But we just wanted to just summarize what the issue is at this point before we moved on to some strategies that you can use. So that first point that students really struggle to transfer that knowledge and understanding from maths to science, they're not vaccinated in maths. We need to help them with the application. So they've got the foundational understanding, but the application is our responsibility, shared with the maths department as well. We can give them that contextualized, piece as well to help support with that process. That assumption that they've got the skills from their maths lesson, that vaccination issue, the fact that it's difficult to apply maths understanding to exam questions in particular, particularly when you add stress to that mix too. We assume that science teachers are A, confident at teaching maths, and B, have the pedagogical content knowledge to teach maths, which is not always the case. We don't necessarily know what the maths misconceptions are. And Mandy and I have discovered relatively recently difficult to find mathematical misconceptions as well. There's very little out there that summarises those. And that's another project that Mandy and I are currently working on, isn't it?
Yeah.
Um, the turnover of staff is an issue as well. So even if you work on this as a department, every time you have a turnover of staff and new people coming in, you need to rework on it and revisit it. Lack of time to engage with your maths department. So it's really difficult to engage within your own department because of a lack of time, but also that discussion between departments is difficult as well. So asking senior leaders within your school to provide time for that to take place is really important. Maths and science is an issue. Students are losing marks on exams because of it. So therefore you can justify asking for time to be able to work on this to improve outcomes.
And actually having some concrete outcomes from any discussions you have with maths leaders and science leaders, because quite often we just have a good old chat about the problems and then nothing changes. I think
Yeah.
it's
And it tends to get exclusively focused on lines of best fit,
yeah,
rather than all these other issues that are coming up as well, which we listed in an earlier slide.
yeah.
So, on to strategies then. How can we support students with transferring knowledge about graphs in particular between maths and science?
Yeah, so here's a graph from a maths lesson, and if you look at that, what are you noticing as a science teacher? What sort of things do you notice? I'll just give you 10 seconds just to mull
Have a
that
think.
over.
Yeah.
No axes labels, yeah,
Hmm.
and, so on. Axes are the same scale.
Yeah.
Well done. Yeah,
And a simple scale as well.
very simple,
Mm.
very simple scale. Coordinates,
Yeah.
yes, absolutely. So if you look at that, it's been plotted and drawn on a block paper. And we've talked to so many maths teachers, and their exercise books are all block paper. And when they draw graphs, they tend to draw it on block paper. So it's knowing, do your maths department actually use graph paper like we do? Or are they always using block paper? Because if they're always using block paper, they do in primary school, you need to explain how to use a piece of graph paper, because actually for some students it's quite tricky. As you said, the same scales in maths, they often do have the same scales, the intervals are the same, and so on. And they use coordinates. They talk about XY coordinates or even ordered pairs. So their data is often very ordered. So you know which is the X and you know which is the Y and you know which to plot it on there. But actually, the same concepts apply in science, don't they? We might have a graph, for example, that is its height of drop versus the height of bounce. And the same point basically means that when the height of drop was 4 meters, the height of the bounce was 1 meters. But you can see how students would not be able to interpret that as being exactly the same. The way we explain it is very different to how it happens in maths quite often. It's obvious to us, but it's not to the students. And so they're not connecting it, they're not transferring this knowledge across. They don't recognise it.
No.
So,
It's also worth considering when students are taught coordinates, isn't it? So they cover coordinates in primary school. So they should come to us in year seven knowing how to plot coordinates on a simple graph like this. Mm.
yeah. Helen in the chat's made a point about decent graph paper. Quite often you'll find graph paper is photocopied as well,
Mm.
especially on test papers and so on and so forth. And it's making sure that the graph paper, you really can read what those um, lines, the small squares mean, and so on and so forth in terms of that.
Mm.
Anyway, the next slide is a potential scaffold to help this problem that I've just shown you here. It's helping students work from a table of results to a graph. And, it's a scaffold. So we've got the table there, height of drop, height of bounce. And we talk about the variables, that the height of drop is the independent variable, and, that would go on the x-axis in most cases. And the height of bounce is the dependent. So actually drawing those lines on your white paper and, really exaggerating it, if you like, you might feel like you're really, battering the obvious, but actually it helps. and then circling a row and looking at those ordered pairs that they would be called in maths, or the XY coordinates, and showing students that the 40 is the independent variable, and you go along the bottom there and up, and actually, doing that with a ruler on the board, and 35 is the Y coordinate, and actually really showing them, this scaffold, and talking them through it really.
Mm. And it's worth understanding as well because we've done quite a bit on gradients relatively recently, and in the maths department they talk about run and rise, which is quite interesting. So the x-axis is the run, and then the y-axis is the rise. So even language like that, it's quite useful to make links between the science department and the maths department. Yeah.
Yeah, yeah. I've heard some people talk about it going up the stairs and things like that. And if that's what's happening in maths, then you need to know what they're saying really.
Yeah. Now, another issue with really sticking with graphs is students really struggle to be able to describe a graph versus explain a graph. They often mix those two up, and we've got a strategy here that works quite nicely for dealing with this. So this is disciplinary literacy linked to maths and science. So being able to interpret a graph is maths and science. Understanding the command words and being able to answer that effectively is disciplinary literacy. But all that you do here is you take a graph, any graph, so you could pull a graph off a past paper, for example, stick it in the middle of an A4 or A5 sheet of paper, and on one side you ask them to describe what's going on, and then on the other side you ask them to explain what's going on. And you can see there, I've described the trend. So the higher the concentration of hydrochloric acid, the faster the rate of reaction. So I've gone straight for the overall trend. You could have a precursor sentence there talking about volume of gas in centimetre cubed, and then moving to that rate of reaction statement. And then on the explain side, we've started with because, and we've included a couple of connectives there to show the link between describe and explain. So forcibly making them differentiate between the two and understand that there's a difference between the two when we describe, when we're interpreting a graph, and we explain when we're interpreting a graph, are two completely different skills, and thinking about that carefully. So that's quite a nice strategy as well. Works really well as a tool for understanding graphs and how to interpret them.
And I think in this one, there's no numbers, so it's a qualitative graph.
Mm,
And those of you that are old like me might remember the old ISAs, where the paper two always had a qualitative graph on it that students had to do something with. The benefit of a qualitative graph is you can really see whether they understand the trends or the patterns that are happening in this case in the reaction. You can link the graph to their understanding.
mm. Yeah, a really good point actually. And then moving on to a quantitative graph. Now this is it's going to be a little bit overwhelming when it initially comes on screen. Um, but this is what you'd call a low threshold, high ceiling task. So this time, instead of having those prompts of describe and explain, you just literally put the graph into the middle of the sheet of paper and you ask them to analyze it, to interpret it. And this is a velocity time graph. And I've just basically scribbled all over it all of the potential things that I could do with this graph, all the information I could find out with this graph. And you can see how a higher level student would be able to do all of that without prompting. Other students, you might say, right, I want you to find the acceleration, find the distance travelled. I want you to describe what's happening in terms of this graph. So it's a low threshold, high ceiling task because everybody should be able to do something, but it doesn't limit the top end. So it's an open task, basically, we would have called it back in the day. And it's useful because it helps you spot misconceptions, spot common errors, spot where students are forgetting information that they might not realise that they've got it. And actually, this was trending on TikTok. I don't know exactly when because I'm not a TikToker, but apparently it's called blurting, where you just write down everything you know about something, and then you go back to your notes and determine what's missing or what was wrong, and then you revise those elements. So
Mm.
this is a low threshold, high ceiling blurting task, which is always a bonus,
Yeah,
isn't
and
it?
it's really adaptive teaching as well,
It
isn't
is,
it? It
yeah.
gives you the time to, because your high achievers can do all those calculations and so on, maybe with a little bit of prompting
Mm.
as you wander around, but then it gives you a little bit of time to help those that need a little bit more help to get started.
And common misconception that might come up on this example is when they calculate the total distance, because they're finding the area underneath the line, they
Mhm.
think it should be meters squared instead of meters when they're calculating the total distance. That's a common misconception, for example, that you might look out for.
Mm.
But yes, a little bit overwhelming because it's all my handwriting on a sheet of paper, but it is useful.
Yes.
Mm. Okay. So this is another strategy, isn't it, Mandy?
Yeah, yeah. So think aloud again. EEF, Education Endowment Fund. If you've not come across it, I think there'll be a link in the chat coming up. But basically, it was something that was found to work in both maths and in English. As you know, it's quite unusual to get a strategy that works in both of those equally as well. And of course, therefore, it works well in science too. And it's basically, it does what it says on the tin. It's you talking about what's going on in your head. I am thinking about this. I've come across this before when we did that. This is what I did then, so I'm going to apply it to this particular problem. I can see there's this unit and I've got to convert it to that unit. You're just thinking through out loud to students. You're modeling what's going on in your head so that they can see it, basically, how an expert does it in terms of that, isn't it?
Yeah, it's really useful. And this is quite an interesting link to that. So we're still thinking about think aloud. And this is often attributed to Maslow, but it isn't Maslow that it's actually linked to. But it's a process of thinking about competence. And the easiest way to explain it is to link it to driving. And we start in the purple box. So initially, before you learn to drive, you're unconsciously incompetent. So in other words, if you were to get behind the wheel, you would be absolutely rubbish at driving, but you wouldn't necessarily think that, particularly if you are a very confident young person. So you're unconsciously incompetent at driving. As soon as you start your driving lessons, you become consciously incompetent. You realize you're rubbish rubbish at driving. And your driving instructor has to remind you every 30 seconds to do various things, including looking at your mirror and indicating and changing gear and whatever. So that's where you become consciously incompetent. Then, as you're learning, you carry on learning, carry on having your lessons, and you become consciously competent. In other words, you are driving well or reasonably well, but you're having to think about everything. I'm now changing into second gear. I'm now going into third gear. I'm now checking my mirror. I'm now doing this, that, and the other. So you're really thinking about it, and it's taking some effort. After you've been driving for a while, you become unconsciously competent. So you will drive to work in the morning and have forgotten completely the journey in between because you'd have just gone on automatic pilot and just got yourself there. So you're competent at driving, but you don't have to think about it in a great deal of detail. Now, as science teachers and teachers of maths in science, we are often unconsciously competent. So we can problem solve a maths-based question in science quite quickly and easily without really having to think about it overly much. And when we do think aloud, sometimes we forget that we're jumping steps that the children in front of us wouldn't know because the children in front of us are consciously incompetent. So they are in that yellow box and we are in the blue box. When we do think aloud, we need to move backwards into the green box and be really conscious as though we were the driving instructor, explaining step by step precisely what they need to do. So, not referring to the mark scheme or things like that, talking through the procedure of what's going on in our head as we're answering that question. So, when you're doing Think Aloud, you need to revert from unconsciously competent to consciously competent in order for it to be effective. Now, we've got an example here. Now, I love this question. It's from an OCR paper from a long time ago. And I want you to imagine you've got this underneath a visualizer or you've projected it onto the board and you're going to write by hand and you're going to do Think Aloud with this question. So have a look at it and think about, read it to yourself and think about what's going on in your head and what might be going on in the children's head as you read through it. So I'll just give you a moment just to do that. Now I know when I've done this question with quite a large number of students in different cohorts, and I know the reason I've chosen that question is because the first two words. So as soon as a lot of children see the word succinic acid, then they'll think, I don't know what succinic acid is. I don't remember having ever been taught what succinic acid is. Therefore, I can't answer this question and move on to the next question. And that's quite a common reaction, particularly for those less confident students and particularly for foundation tier. So if I was going through this process and explaining it, I would firstly say, well, succinic acid is a substance. I don't need to worry about what substance it is. I just need to know it's a substance. And then I move on to has a melting point. So in my head, I'm thinking melting means it's going from a solid to a liquid. And the melt is happening at 184 degrees Celsius. So thinking about what's going on in my head as I'm going through. Now, I've got an annotated example here that I use with a group of students. So you can see I've gone through and I've written down what's going on in my head as I've been thinking through the problem. I've talked to them. I've shown really clearly that there are two parts to the question. Firstly, I need to decide is it solid, liquid, or gas? And secondly, I need to explain why. So I know the connective because is really important in my answer. I've used a mathematical manipulative to help me problem solve. I've used this number line to help me answer. And I wrote that number line and talked through what was going on and how I produced that number line over time. And we did this at a training event, didn't we, Mandy? And
Yeah, we did.
there was a representative from OCR there at the time. And she suggested if you're doing number lines like this and it's to do with temperature, you might want to switch it from being horizontal to vertical. So it's more like a thermometer, and that might
Mm.
help students visualize and understand as well. But you can see also I've made a mistake on there and I've crossed it through, and that's important too. It's important that you're doing this by hand and not just projecting the answer up or projecting the mark scheme up, that you're physically writing the answer to the question and showing your thinking, showing it's okay to make a mistake. I've put a line through it. It's okay to go on to underneath the line because that will be scanned through. I've made sure that I've started there with because. I could have put because straight after the solid, but I separated it out for understanding purposes. So thinking about how you go about modeling your thinking is really important. So that's an example. So that's another strategy. That's think aloud. So going on to the next one is called fading.
Fading, yes, and we all use worked examples, in our lessons, don't we? Well, it turns out that the research shows that just one worked example is not enough. Going straight from that to actually answering a question is usually too big a stretch. And so what Bob Pritchard does in his blog, and again, we've got a link, thank you, for that, is to do some fading. And fading is where where's Karen gone? There she is.
Sorry, sneezing,
So,
sorry.
so example one, just look at example one. So we've got a question there. and the teacher has gone through thinking aloud and worked out the answer and sort of laid it out really nicely as well, in terms of that. And actually, just on that point, one of the comments from the maths GCSE this year was that a lot of students lost marks because of their poor laying out of their answers. The examiners couldn't work out what was going on, or they didn't include their working out. We learnt an interesting thing
Mm.
at the ASE conference, that there are two command words: determine and calculate. And there is a significant difference between the two. I genuinely
Mm.
didn't know this.
You can't
Um,
tell by looking at the definitions either.
no, no. So we did give them a bit of grief. But determine, you won't get the answer. You won't get the marks if you just put the correct answer. You have to show your working out for determine, whereas calculate, if you don't put any working out and just put the correct answer, you'll get the full marks for it. So just bear that in mind if you're at AQA exam board. Anyway, back to this. I digress. So the first example is fully worked through. Okay, and then we've got a second example again that's fully worked through. Slightly different context, and then we start to fade. And so the example one about the goat there, you can see that it's been laid out in exactly the same way, but they've faded from below. Okay, so the answers need to be worked through to get there. So we've faded from below, and then there's a second example there where even more fading has happened. And the research shows that if you do your worked examples but fade from below, that is really beneficial in terms of that. And actually, in our book, the Maths and Science book, oh, you can't see it because my background's
This
blurred,
one.
but the Maths and Science book, that was one of the premises that we did, how we wrote the book. We've done worked examples, and then we've done faded examples, and then we've done lots of questions for biology, chemistry, and physics for the whole of most of the GCSE curriculum for AQA. So this is the premise in terms of fading from below. He also talks about FAME, F-A-M-E. So the F is fading, the A stands for alternate, I do, you do, and then M, mistakes. Now, when students are confident, and the key is confident in their understanding, you can show them an example where somebody's got the wrong answer, and you really over the top and say this is the wrong answer. Explain how it's a wrong answer, and the students then look through and then they work out where the mistake has been made, and then they would correct it, they would do it correctly. So that's M, but the students need to be confident in that. That's for the sort of the next layer up. But in terms of adaptive teaching, while you're helping one group, they can be doing that. And the E is for explain, so explaining how to approach a mathematical problem as well. So in terms of that.
Okay, so this next bit's a bit shocking, actually, isn't
Oh, this
it?
next one, yes. I was looking through the national maths website, and I came across this, and they've done a whole load of research with lots and lots of different questions. But look at this: you've got to ring the option which gives the biggest answer. So in A, it's 8 multiplied by 4 or 8 divided by 4, and they had to ring which one gave the biggest answer. And then the same for B and C. And here are the results from that, which is quite shocking. So we've got the different ages across the top there that they did it with. Getting the right answers, which is multiply, divide, and divide for A, B, and C. If you look at the 15-year-olds, only 18% of them got those 3 questions correct. And at the bottom there, students that answered all 3 as multiplication, 30% of 15-year-olds that they studied, and it was a big study, 30% of them answered that all multiplication was the correct answer there, which of
Mm.
course it wasn't. Um, which is basically showing this misconception that multiplication makes numbers bigger.
Mm.
Um, and
And you might be thinking, well, why is that important in science? It's really important when it comes to when it
yes,
comes to talking about quadrats.
yeah, absolutely.
Um, so quite often when we're doing quadrats and we're finding areas of a field, for example, areas of quadrats, we're dealing with decimals, and students might be thinking about, well, what is the area of a quadrat? And they might be getting it wrong because they might not realize that if you multiply zero point 0.5 by zero point 0.5, you come up with 0.25. And one of the ways of helping support students with this is about putting it into words. So when you see zero point 0.5 times or multiplied by zero point 0.5, it's like saying a half of a half. And of course, a half of a half is a quarter. But if you support students in a build up to this and talk about the fact, well, what's a half of 8? What's a half of 4? What's a half of a half? And they can see that that's the case. You can add complication to this by changing the units in addition. So this is another problem that students have is when they multiply up, they if they're doing it in centimeter cubed, they might assume centimeter squared, sorry, they might assume that the answer C is correct for this second example when it's in fact B, because they struggle with that conversion of units and understanding that there's 1,000 centimeter cubed. We're dealing with in the thousands rather than in the hundreds here. Um, and that can lead to complications when you've got an area of a field that's in meters squared and maybe the quadrat's in centimeters as well. So there's lots of potential confusion here on ecology questions.
Definitely.
Yeah. And this came up because we did a piece of work for the Education Endowment Fund, didn't we, Mandy?
We did.
Yeah. So we were asked to do this piece of work here, which was looking at how we could use what's called the radar strategy. So this is another strategy that's quite useful, radar. So research, anticipate, diagnose, address, assess, and review. And what it's basically saying is it's important for us to research and anticipate that students might have misconceptions in maths that impact negatively on science. We then can use diagnostic questions to see if students have got this misconception and then address it by talking about it and discussing it and explaining it. And then we need to check, have we resolved this issue? So assess and review is just double checking that we've actually solved the problem. And there's a couple of strategies here on this slide. You will get a copy of the slides at the end, there's a copy of the presentation, sorry, at the end. So you'll have access to these slides. You can see at the beginning we're using a number line there, and at the end we're using visuals in terms of blocks. So there we're using mathematical manipulatives. Remember when we were talking about Johnson's triangle, to help them visualize the problem and help them solve the problem. So that's worth having a look at as well.
This is a favourite question of mine. It actually came off an AS biology paper a long time ago when we did ASs, but I think it demonstrates the issue. So we've got two figures, the height and the width there, and what students were asked to do was calculate the height divided by the width, and so many students put this as the number. This is the answer. Basically because they were doing it on their calculator and just wrote down every number. And there's a big issue there in terms of understanding about significant figures and precision and so on. So if the answer was to three significant figures, because if we look, the height is three significant figures, the width is three significant figures, so therefore we should give the answer really in three significant figures. And so the answer should be 0.494. Which involves some rounding there, as you see. in terms of that. Generally, when we're multiplying or dividing, we tend to use significant figures, and in addition and multiplication, addition and subtraction, we tend to use decimal places. So this should be significant figures here in terms of that.
And it's the two common errors that students were making if they didn't put the whole number on was they would be doing it to two decimal places instead of three significant figures,
Yeah,
or they were rounding incorrectly if they did
yeah.
give it to three significant figures. So significant figures is a problem for students, and we got a nice little quick wake you up quiz here. So we'd like you to just run down. You don't have to write anything in chat or anything, just a quick rundown. How many significant figures are each of those numbers to? And whilst you're doing it, think about which ones would the students have a particular issue with. Let's just give you a moment to do that. And I'll pop up the answers. And there might be a question about one of them. The issue that many students will have will be on the 0.005 versus the 0.00500 or 00. But also the one just before the bottom as well might be problematic too. So significant figures, when you're trying to explain to students how to work out the number of significant figures, and you might be thinking, well, they're having problems with this in the classroom. So what we need to do is teach them how to do significant figures. So what are the rules around significant figures? So Mandy and I did a bit of research, didn't we? And these are the rules. Just give you a moment to read them. Confusing. You try and explain those to students, particularly when you get to the bottom with the numbers 300 and 380 versus 58 and 470, etc. So we've come up with an animated slide which actually helps with this. So we've got a number here. This number here is not a significant figure. And normally if we're face to face, we would ask the audience why that was the case. But we won't do that here just because of the situation. So the reason that is not significant is because it's what we call a leading zero. So it would be equivalent to us writing 0.0000529, for example, and we'd ignore those zeros because they're leading. This is the first significant figure, and the reason it's the first significant figure is because it's the first non-zero digit. This zero is the second significant figure. So even though it's a zero, it is significant, and this is because it's between two non-zero digits. And then the zero at the end is a significant figure, and this is because it's a trailing zero and it comes after a decimal point. We've got a decimal point in place, so that's why it's significant. So using a slide like this can help students understand how you work out significant figures rather than using those rules. But there are added other complications involved in this too.
So quite a lot of students think that decimal places and significant figures mean the same thing, and of course they don't. So you need to show them that they are very different. Now I usually do this with lengths of chocolate and so on, but here we go. So if I've got 4.2 millimeters, for example, and I want to convert it into meters to two significant figures, that would be 0.0042 meters to two significant figures. Now let's do it to decimal places. So if we look at 0.0042 meters, that is 0.00 meters to two decimal places. And students are quite shocked by that and realise that there is a difference. So it's using strategies like this to show them the differences if they've got that issue in terms of thinking that they are exactly the same. And the significant figures, the reason we use them obviously is that they preserve the precision regardless of the unit.
Mm. which is
And
important in science, yeah. And then in terms of rounding,
again, rounding is a common misconception, that they lose this significant figure, because they think it's a zero placeholder. Now, if I asked you to round, if I asked you to do 6.99 times 10 to the power of 5, to two significant figures, what students tend to do is they find it irresistible to go, oh, it's 7 times 10 to the power of 5. But that obviously is to one significant figure. We need the decimal point and the zero to be to two significant figures. So it's checking those, misconceptions, and making sure students can do that as well.
mm. Now, a number of you mentioned converting units, didn't you? And I think, was it last year's ASE, Mandy? You came across the double number line.
Yes, yeah,
Mm.
or the year before maybe, actually, yeah,
Yeah.
I think, yeah.
Mm.
So if you look at this question, a student collected 2.40 grams of sodium chloride or 150 centimetre cubed of salty water. What is the concentration of sodium chloride in grams per decimetre cube? So they've obviously got to do some calculations and change units there. And this was an exam question, and pretty much it was left blank by most students. Many of them were able to write the equation there from the top, how to get started. And then what I would do, I mean, I personally like to put in the units in red. I think Karen, you were not sure about that, but I like it because it just makes it obvious what units we're doing. I would think aloud and talk this through and write the sum out, doing the substitution from the question. And then I would draw two lines. We all know that there's 1,000 centimetre cubes, and in 1 decimetre cube, sorry. So I draw two lines, parallel lines, and put 1,000 and 1 and naught underneath each other. Then I would divide it into two. So I've got 500 centimetre cubes, which is therefore 0.5 decimetre cubed. And then I would divide the centimetre cubed into hundreds, and the corresponding decimetre cubed. And then I'd put in the 150 there and go, right, okay, so what is that in decimetre cubed? And they can easily find that out. They can do that conversion, and then they can do the sum. And it's the double number line is a great manipulative for doing unit conversions, and enabling them to see the relationships between the two units.
Mm. And obviously it's a form of scaffolding, so over time you'd hope they wouldn't need to use that on the exam by the time you got there, but it would be there as a tool if they felt they needed to.
Yeah.
Because often they forget, they don't know whether to multiply or divide by 1,000. That tends to be the problem when they're
Yes,
converting
that's the
units.
issue.
Yeah,
Yeah.
and this helps solve that problem.
Yeah.
Yeah, so there was a number of different strategies there and a number of different ideas which we will hope that you will take away from this. So that includes things like making sure you're not assuming they're vaccinated with their maths, thinking about the macro, how are you going to use manipulatives that can help support with the maths in science, using think aloud and fading as different strategies, thinking about place value, so that's thinking about where the decimal point is and where the numbers are, significant figures, borrowing from maths and sharing with maths, and using language like they do in maths, so things like integer digits and numbers and that kind of thing. And also, if you're interested, just those two texts that are available there. And the Collins was out, was that November? I think that came
Yeah.
out in November.
Something like that.
And there's a sample. If you go onto the Collins website, you can see a sample of the ratio chapter, so you can see what a chapter looks like.
Yeah.
So hopefully you found that useful. There's our contact details if you would like those. But if you've got any questions, we're happy to answer them if you want to pop anything in chat. And yes, you'll get a copy of the recording. There you go. And you've
Yeah.
got a link there.
And there's the poll as well, the final poll.
Oh, yes, let's have the
Karen.
final poll. Yes.
So.
Are you more or less confident than when you came to us?
Oh dear.
Thank you, everyone. Yeah, if you could just do the poll, that would be amazing. Oh, thank you, Blessing. Yeah,
Thank you.
thank you.
Thank you. Helen talked about the Isaac physics site as being
Ah,
really
yes,
useful.
very Isaac.
Yeah,
They do more science. They do chemistry as well, don't they? Do they do biology? So very good, Isaac. Yeah,
cool.
lovely. Thank you.
There we
Oh,
go.
excellent. Thank you
That's
so
really
much.
good. That's good. That's good.
We've shown improvement. Hurrah.
Yeah.
Well,
But
thank you very much for joining us. Feel free to stay and ask questions in chat if you think that'd be useful. But if not, thank you very much for joining us and enjoy the rest of your evening. Yeah, I don't think there are any questions. So thank you very much, everyone.
thank you, everyone.